Okay, hi everyone. Um, I know there has been some changes and there has been some kind of confusion going on, but we'll try to figure the schedule out and just letting you know that after whenever we have a lecture, I'm guessing that's being done at home. And during class time, you guys discuss what's going on, or you guys work on a class activity together, right? And afterwards, we do have a Q&A session. I believe that's at, let me think, 11 o'clock there. I'm not too sure because I know here it's 6 a.m. So please take advantage of it. If you have any questions, or if even if you don't, we can have uh, a Skype meeting together and seeing if everyone's on the same page. Okay, so that's pretty much our goal. And starting today, we're gonna move on to a different chapter. And this is the probability chapter. And as I mentioned before, this is very, very different from all the stuff that we learned so far. So if you are a little behind, or if you have any homeworks or assignments to catch up on, just do that because we're going to move on relatively slowly compared to the previous lessons. So take advantage of that. So work on your previous assignments and keep up with it because after we're done with this chapter, we're going to tie everything back together, the stuff that we learned so far, mean average, standard deviation, and we're going to use those concepts a lot. So those are going to come into place again. So please review those topics and at the same time keep up with this chapter as well. Probability is the fundamental uh, I would say the foundation of statistics. So this is very important that you understand this concept. And I'm pretty sure you're familiar with this because this out of statistics probability is pretty used often in math or um, even like computer science. So that's something that's pretty common and it's pretty prevalent in math related subjects. So it shouldn't be that hard. It's just a lot of thinking and maybe some being creative at times, right? So let's just define some definition. Okay, so let me just choose my pen. Okay. All right. So first, we have to make sure that we understand what probability means. All right. So let's. Okay. So when we talk about probability, we can easily find this in our daily lives. For example, if the weather forecast says, "Oh, it's going to rain today," with a probability of 70%, that means that there is a chance, 70% chance that it's going to rain, right? So that's how probability pretty much works, and probability um, is okay is if you're looking at the definition of probability. Oops. Okay, let me just come back with. Alright, so sorry about that. So if we're defining the definition of probability, alright, so probability of an event is viewed as a numerical measure of the chance that an event will occur. Okay, so it's naturally relevant to the situation where the outcome of an experiment or observation exhibits variation. So, for example, so say for instance, we're flipping a coin. And if we're flipping a coin without a bias, right? There is a 50% chance that it's going to show up in head and tail, right? And these two are equally likely, meaning that each of the event, right, will happen 50% of the time, right? So these concept of probability using percentage is used very often. Um, Before we go into that, let's just get some more definition, right? So next up is experiment. Okay, experiment is the process of observing a phenomena that has variation in its outcomes. Okay? So it's a process of observing a phenomenon that has variation in its outcomes. And again, we can take the example of flipping a coin because we get a head and tail. So it's never, it's never the same. It's never um, the same outcome, right? So there is a variation in its outcomes, and that's what we call an experiment. Okay. Um, and an event right is the set of elementary outcomes possessing a designated feature. Okay, so say we're assigning an event. We're taking the coin example. We can say that here event A. We can say that uh, that the event is when the outcome is heads instead of tails. Okay, so that could be an example. Um, and alright, let me just write it down. Getting heads. Okay, sample space alright, is the collection of all possible outcomes, possible distinct outcomes of an experiment. Experiment. Okay? And here the sample space of the experiment of flipping a coin would be what? Right, so would be either getting a head or tail. Right? So these two are the all possible outcomes for the experiment when flipping a coin. Okay? Um, let's see if there's anything else. Okay, so let's look at an example. Right, we talked about coin flipping. And let's take another step further and say that we're tossing a coin twice. Okay? And so the outcomes here, we're looking at, so first trial, first toss, and we have second toss. So it could be either head or tail. And the second also can either be head or tail, head or tail. Correct? So the list, it could be head head, head tail, tail head, and tail tail. So these are all possible outcomes. So the sample space, we denote the sample space by S, is HH, HT, TH, and TT. These are all the sample space, all possible outcome, right? And if we're saying, if we're looking at an event, let's say that we're looking at event A, right? And A is getting exactly one head, right? Event A is getting exactly one head, and we do have those outcomes, so we would denote it by A equals, where do we have exactly one head? HT and TH, right? So you would write that down. So that would be HT and TH. So in total, we have two possibilities, right? And we call that an event. Alright, so that was an example of uh, uh, tossing a coin twice, and that we call an experiment. So those are the definitions, and let's now look into another example that um, could possibly help us understand. Okay. Um, okay. Before we do that, we have another definition to note, and that is probability of an event. Okay, so this is exactly what we talked about before, or just the probability, right? We said that it might rain 70%. That means that it has a chance of raining, right? 70% of the time. So this is a numerical value that represents the proportion of the times the event is expected to occur, right? So let me just write that down. Numerical value that represents the proportion of times the event is expected to occur. When the experiment is repeated many times under identical conditions. Alright, so this is something that we are going to see, because probability of an event, like you can't really say what will happen just by doing an experiment once. Okay, that's why if we're looking at the tossing a coin example, right? For example, tossing a coin. So if you're doing this experiment, we're going to literally toss a coin, say 100 times or 1,000 times, and we're going to record it. So if we flip it and if we get a head, we record it as head and tail, and we repeat them many times under identical conditions, and we write down how many times it occurs. So um, for example, if you do 1,000 times, um, right? If we did 1,000 times and we got heads 499 times and 501 times, right? The percentage, the probability of getting a head, according to this experiment, is 0.499. And according to this experiment, it's 501. Right? These are the probabilities according to the experiment, and that's how we get the probability. But if we were to do this infinitely many times, like as the number of trials increase up to infinity, it's going to be very close to zero point 0.5, because if there is no bias, meaning that if the two sides are equally likely to happen, then it's going to be zero point 0.5. Okay, so that's that. And probability of an event. For example, if we're looking at probability of event A occurring, we would denote it as P parenthesis A. So this is the probability of event A occurring. Okay? Alright, so that's what we wanted to discuss. So we're essentially looking at the proportion when we're talking about probability, right? And let's look at some of the rules, or the laws rather, of probability. Okay, so probability. So first of all, probability has to be greater than or equal to 0 and less than or equal to 1. Right? So 1 meaning it's happening no matter what. So it's happening if you do that, or if you do this, it's happening all the time. And 0 meaning it never happens. Right? So that will be the probability of 0. And second law is that P of A, probability of event A occurring, is all individual events in A occurring. So all summed up. So for example, say that before we said that tossing a coin twice, we got the result of sample space of HH, HT, TH, and TT. And see that event A is getting exactly one head. That means that we're including this and this, right? So we would count those as individual elements, right? E1, E2, E3, and E4. So if we sum that up, it comes out to be 2. But there are 4 possible outcomes, and out of those, we're choosing only 2. So that's going to be 2 out of 4. That's 1/2. Alright, and always probability of the sample occurring, right? Everything, the probability has to add up to 1. It can never be greater than 1. Alright, so these are the properties of probability. Okay, so let's look at an example. Alright. So yeah, we do have a formula that, I mean, I'm pretty sure you already know this, but I'm just going to write this down. This is number of sample points associated with A over total number of sample points or sample space. Okay, so I'm trying to see if there is any interesting example. Alright, so let's look at this. Uh, um, for probability, at least for this lecture, there won't be that much of an Excel use because this is um, pure calculation. Okay? Alright, so say we're looking at an example. Say a card is drawn from an ordinary deck. Alright, so ordinary deck has how many cards in total? 52 cards. That's the ordinary deck when we're by default. And we're assigning events. Let A be an event of getting an ace. Okay? And let B the event of getting a red card. Okay? And let's see be the event of getting a black queen. Right? And we're going to find the probabilities of these occurrence of events A, B, and C. Okay? So I'll give you I guess I give you a minute to work on it. So just do that and let's talk about this. Okay? Okay, so looking at probability of A. So this is a very simple example. Alright, so probability of A equals what? Getting an ace. How many aces are there in an ordinary deck? We have four different suits: spade, club, heart, and diamond. So that comes out to be four different aces. So that's going to be 4 out of 52. Getting a red card. Okay, so probability of B happening is only, so think about it. Red card can be heart and diamond. So that's half of the time because there are four different suits. And for getting a black queen meaning clubs and spade, so that comes out to be total of 2 cards. So that's 2 out of 52, and these are all probabilities. Okay? Alright, so that was an example of that. And let's move on to something else. Okay, so there. Okay, so we're gonna continue our discussion of probability, and we're now going to move on to probability using Venn diagram. Okay, so I'm pretty sure you guys have already seen this before, so I don't think this is going to be something new, but this is a way of calculating probability. Alright, so this is called the Venn diagram. Alright, so we have complement, union, and intersection. Okay, and to visualize this, we always have this is a sample space, right? Everything is in here, and for example, there is an event A, right? And there is another event B. Okay, so we call this this section right here, we call this what? We call this intersection. Okay, and we call the entire space right here, we call this what? Union. Right? And if we're looking at complement, complement is everything except that except for that event. So if we're saying complement of A, it will be everything but A. So all the space around it here will be a complement. Okay? So let's look at an example. Here, we do have an example using tossing coins, because this is tossing a coin twice. This is our favorite example. So we're going to make a Venn diagram for the experiment of tossing a coin twice, and we're gonna assign events as following: tail, at the second toss, and B, at least one head. Okay, so to list out the sample space, we did this before, so I'm not going to draw the tree diagram, but we have head, 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 tail, tail, head, and tail, tail. Alright, so we have 4 possibilities, and this is a sample space, and there are 2 events. Your tail at the second toss, and B is at least one head. So we're going to draw a Venn diagram. Here we have event A and event B, and sometimes this is not the right Venn diagram, but this is it for this case. So let's look at this. Say that this is for A, tail at second toss, right? So tail at second toss is this and that, right? And it says for B, it's at least one head. So at least one head here, here, and here. And we see an intersection for this element because this is tail at second toss, and since the first trial was head, it's at least one head, right? So we would put that right here. And everything else for A is T, T, and the rest for B is H, H, and TH, right? So that completes the Venn diagram that we have. And this is going to be more useful when we look at an example as follows. But before we before we do that, I'm going to write a notation for these, right? So complement, we notate this as A with a bar, or sometimes we do it like this, but um, this is the older version, and we use a bar on the top of A, and that represents a complement. And for union, we use a UB. Intersection, we use AB or A cup B, right? So these are the notations that we have for the operations. Okay. All right. And we have another definition that we might want to look into. What is the notation here is mutually exclusive. Alright, so mutually exclusive means that when we're talking about event A and B, when A, B, so which means the intersection of A and B is an empty set. Okay, so if we translate this into a simple English term, it means that A and B do not happen together at the same time. Okay, so for example, let me just together simultaneous. Okay, so for example, if you say that event A is okay, so say that let's go down a little. Say that event A is getting ahead. Okay, when we're tossing a coin just once, okay? And B is getting a tail. Right? This doesn't happen, these two events do not happen simultaneously, which means that you cannot get a tail and a head at the same time. That could never happen unless you have some weird type of coin, or sometimes if unless you're a magician, right? And if we were to draw this, right? Oops. If we were to draw this, it would look something like this. Here's A, and here is B, and we don't have any intersection together, right? Okay. Alright, so here comes another law that's pretty obvious. This is called the law of complement. It states the following, right? Event of A is 1 minus probability of complement A, 1 minus probability of complement A. Right? This makes sense because when we're looking at so when we have probability A and we have the sample space, if we subtract what's and this everything else here is the complement. Okay, so this is a complement. If we subtract that from 1, then we are left with just A. So that's simple. And also, let's go a little. Okay. Alright, so we're looking at addition law. right? So if we were looking at probability of A union B, okay, this is probability of A plus probability of B. Well, let's look at this. Let me draw another diagram here so we have a better understanding of what's going on. Right? So here we have A and B, and we're looking at A union B. So this part, we're looking at the circle, right? Well, if we do this, if we add A, okay, let me do this very carefully, and if we add B, what do? We essentially we double count the intersection, right? A and B. So that's why we subtract probability of A cup B, A intersection B. Right? So this is the addition law. And these are pretty straightforward, I think. And this is a case for mutually exclusive for A and B, mutually exclusive. You just have A union B equals A probability of A plus probability of B. Why? Because this becomes 0 if they are mutually exclusive, right? So that's about it. And let's look at an example using what we've learned so far. Alright, so here's an example. Alright, so an English class consists of 22 students, right? And the distribution is as follows: junior, seniors, and here we have women and men. Okay, we have 4, 6, 5, 7, and the instructor randomly picks one person to read his or her composition. Right? What is the probability that it is a woman or a senior? Okay, so randomly picks, and probability that the person is woman or a senior. Okay, so whenever we're looking at word problems, and which is most of the case, we have to be careful with it. So whenever we have or, right, or translates into union. So A or B, it's A union B. So either A or B. And on the other hand, translate into intersection. So if it's A and B, this is straightforward, right? It has to be A and at the same time B. So this is A B or A intersect B. Okay, so probably the person who is picked is a woman or a senior. Alright, so we have to look at this. Why don't we just assign some events here? Right, so that's the first thing that you have to do, assigning events, and it's going to be handy for you later on. I mean, these are really simple problems, but later on, if it gets really complicated, you might want to do that. Alright, so why don't we say that W is a person who was picked is a woman. Okay, and say S is the person who was picked was senior. Alright, so these are two events that are assigned. Alright, so probability that a person picked is a woman or a senior. So if we were to write that down in terms of the notation, that's going to be probability of woman, or translates it into union, so woman or senior. Alright, and we already have this formula. So this is always PW plus P of S minus P of SW. Okay, so yeah, so let's just look into this. What is PW? P of W, probability of woman. Right? Probability of woman is, how many students are there? Total of 22 students. So that's out of 22. And how many women are there? So there are 4 junior women and 6 senior women. So that makes it 10. So it's going to be 10 out of 22. If we're looking at probability of senior, that's out of 22 again. Probability of senior is 6 women, right? And 7 senior men. So that's 6 plus 7, that's 13. And we need one last thing, that is probability of woman and senior. Woman and senior. That's just 6 out of 22. And if we just solve this, it's going to be 10 over 22 plus 13 over 22 minus 6 over 22. And that makes it 23 minus 6. And that is equal to 17 over 22. Right? So this is how you use the laws that we just learned. Right? So that was an example, and let's see if there is anything that we can do here. Okay, I guess we can work on this. This is another example on Venn diagram. Okay, so example. Determining probabilities from those given in Venn diagram. So I'm going to give you a Venn diagram, and you are supposed to come up with the probability according to the diagram. So this is the sample space. Okay, so we have A, we have, oops, change that to B, and we also have AC. Okay, alright, so here the probabilities are 13, 7, 10, 15, 28, and 27. Okay, so to explain a little bit, let me just write down the problems first. Probability of A, probability of B, C, complement. Okay, probability of A union B. Alright, so so here it says 13, right? That's only referring to this outside portion, not including the intersection with B. So this part is only 13. Okay, got that? Alright, so why don't you just work on this? So A is asking for probability of A, B is asking for probability of B and C complement, right? So everything else, not the area of B and C intersection, but everything else, right? And A union B is A or B, right? So we have the formula for this already. So just pause the video and try to work on this and come back to whenever you're ready, right? Okay, so let's work on this. I hope you spend some time thinking about it, or at least a second or two. Okay, so we're looking at probability of A. So probability of A is this whole thing, the whole circle here. So we have probability, pure probability of A, right? That is not intersecting with B, so that's 0.13. And we have another portion of A that is intersecting with B, and that is also part of probability of A, right? So that's 0.07, so this comes out to be 0.20, right? So, and the second one, probability of B and C complement, okay? So, let's look at this. B and C is right here. B and C, this one. Okay? And we're looking at everything else except this. So, everything else, let me just highlight it with this. Everything else. So, it's going to be everything here. Okay? So if you have that, what is it going to be? So, I mean, we learned about the law of complement. If we just scroll up a little. So law of complement states that if we're looking for the complement, where's my... Oh, I don't see my mouse. Okay, here it is. Okay, so if you're looking at the complement, it's always 1 minus that, right? It's 1 minus complement equals the whole. So let's go back. It's not listening to me. Okay, we have to go back. So again, if we were to add probability of A and probability of A complement, the result is always 1. Okay, so that's something to remember. Just flipping the equation, the formula that we have. So this is essentially what we're saying is this is 1 minus probability of B and C, right? Because this is a complement. So that's going to be 1 minus 0.15, or in other words, that's going to be 0.85, right? And let me just give you another part to this. What about this? Probability of B and C complement. Right? So this is what it's saying is this is probability of B and C complement. Okay? So B and C complement. B, okay, I have to choose another color here. So B is right here. B is in yellow. B. Okay? And C, okay, if you choose another color, let's choose, I don't know, pink. Okay. B and C complement, so C is right here, so C complement would be what? Everything but C. I'm not sure if you're seeing this correctly, but what I'm trying to say is that the intersecting part with this, the pink and the yellow, is this part, correct? Because we're looking at the intersection between B and C complement. Alright, let me just draw another diagram, as this is getting very messy. I'm gonna draw another one here. Okay, so this is A, this is B, and this is C. Okay, and we're looking at B. Let me do this again. B, and again, this is an intersection, so we're looking for overlap of yellow and this is C complement, so C, everything but C. So okay, C complement. Right? And what's the overlapping part? Again, this part. This is where it's overlapping. Right? So if we go back to the original diagram and look at the probabilities there, that's here 0.7 and 0.10. So this is going to be, where is my pen? Oh, here. 0.07 plus 0.10, that's going to be 0.17. Okay? Alright, so now if we were looking at A and B union, right, that's A, probability of A plus probability of B minus probability of AB, right? Or we can just do, since we have different probabilities here, we can just add these numbers. So here we have 0.13, 0.07, and 0.10. So if you just simply add those numbers, you're going to end up with 0.10 plus 0.07 plus So from here, from A, okay, let me erase this so we don't get confused. Okay. Right, so 0.13 plus 0.07 plus 0.10, and also this part is part of B, so plus 0.15. And if you do that, 0.2 and 0.3, that's going to be 0.45. Okay, so that's how you use Venn diagram, right? Okay, so that's about it for Venn diagram. I'm going to give you another example. So using the same diagram, but I will draw this again. So same diagram, look for the following areas, okay? So here we have another example. This diagram looks exactly the same as the one before, but we have different questions here. So for part A, you're supposed to find the intersection between B and C. For B, it's B complement and C. And this is the part where it says probability of exactly one of the three events occurring. Okay, exactly one. So just work on that and come back to the video once you're done. Right? So pause the video right now and work on it. Okay, so I hope you're all done with this, and this is pretty easy, right? Probability of B and C occurring at the same time. That's this overlap between B and C. That's going to be 0.15. And here it's asking for probability of B complement. Okay, so let's highlight this again. B complement. So everything here is B complement and C. And C is this part. So we're looking at the overlap between the blue and the yellow, so which makes it green. So we see it clearly, right? So that's going to be this part. That's 0.28. And part C, probability of exactly one of the three events occurring. So one of the three events, if you're looking at A, right? Which probability is it just A occurring, not A with something else, but just A. That's going to be 13.13 because 0.07 is A and B, so we have two events occurring at the same time. So this is for A it's 0.13, and for B exactly one of the events. Again, 0.07 is A and B, and 0.15 here is B and C. So the rest, which is 0.10, is just B, probability for just B. Alright, so same for C, 0.15 is B and C, and the rest, 0.28, is for just C. So if you add that up, it's going to be 23, 28, so that's going to be 50.51. Okay, so those were the examples for Venn diagram. Alright, so now we're going to move on to the idea of independence. Okay, and this idea of independence is very, very, very important in probability because it pretty much serves as an assumption, the baseline for all the probability questions or anything that comes up in probability. Right? So let's look at this. So independence. Alright, so independence is actually very, very advanced topic. So if you go into more advanced text, they're going to talk about some more advanced mathematical stuff. But here, it's sufficient for us to declare it as two events that are not dependent on each other. Right? So we say that two events, say A and B, are said to be independent when the two events do not depend on each other. Okay, so for example, if we say that we, for I don't know, for let's say for an Olympic game, right? Winning a 500-meter track. So let's see. Winning we're talking about track game in Olympics. So winning a 500-meter race versus winning a 1,000-meter race. These two are independent because winning a 500-meter race does not depend on winning a 1,000-meter race. Okay, so another just simple example, it's just going back to our coin flipping. If we were to flip coin twice, the first trial does not affect the result of the second trial. Correct? So you get equal chance for both. So say for first you have head and tail, and similarly for second round you have head and tail, equal probability, right? So that's what it means by independence. But in mathematical terms, when we're talking about independence, we state the following. Okay, so we say that two events are independent when probability of A and B equals probability of A times probability of B. Right? This is if A and B are independent. Okay? So for example, if we have probability if so say we have different events. So say we have A1, A2. These are all different events up to AN. Then probability of AN, A1, A2, A3, dot dot dot, AN is simply the product of all these probabilities if they're independent. Okay? Alright, so let's look at an example. Okay, so now we're looking at something different. Let's look at this example. Right? A die is rolled 3 times. Okay? And we're looking for the probability of obtaining 3 sixes. Okay? So die, a die has 6 sides, right? And each one has 1 through 6. So we're talking about getting 3 sixes. Okay? And we have to think about the idea of independence. Are these die rolls independent? Just think about it. If you roll a die once, does it affect the second trial? No. So this is, the rolls are independent. And if we claim independence, it's going to be very easy for most of the problems. So each roll is independent of the other rolls. Okay, so probability of getting a 6, let's see, 6 is 1 out of 6, because you have 6 sides and you only have 1 6, so that's 1/6. And now we're talking about 3 sixes, so that's going to be 6 times 1 6 times 1 6, because they are independent. Okay. All right. So let's why don't we just look at some examples. Okay, so let's do that first. Okay, so these are the problems that I included in your class activity worksheet. So there are 4 questions, and I copy them down here. So just go through them and try to answer as many questions as possible. Take as much time as you want, and just come back to it. So pause the video right now and work on those problems. And once you're done, just come back to it, right? And we'll discuss how to do this. Okay. Alright, so I hope you all worked on it. So let's just look at these examples. Some of these are really easy, so we're just gonna skim through it. So a single card is drawn from a deck, and we already established that a deck has 52 cards. And let me just write them down. So we have clubs. What do we have? We have spade, heart, and diamond. And for each of these, we have numbers A's through 10, and then we have J, Q, K, right? So these are the ones that we have, and then if you add these up, we end up getting 52 cards. All right, so find the probability that it is. So a single card is a king. So king, there are 4 kings, right, from each suit. So club, spade, and spade, heart, and diamond. So that's going to be 4 out of 52, right? A king or a 10. Alright, so we see a or, right? So why don't we just work on the assignment of events? So why don't we just say probability of, no, let me just go back. So say K is getting a king and T is getting a 10, right? And we're looking for probability of king and 10. So this is going to be P of K plus P of T minus P of KT. However, if we're looking at these two events are mutually exclusive. Yeah, exclusive, meaning that it's never going to happen simultaneously. It's never possible to get a king and at the same time you get a 10. No. So this is going to be 0. So if you just add these two probabilities, there are 4 kings and there are 4 tens. So that ends up being 8 over 52. This is the answer to part B. Okay, and heart of a 10, right? If you're looking for a heart of a 10, there is only one of these, so this is going to be 1 out of 52, right? A heart of a spade. Alright, so part D, we're looking at a heart or a spade. Alright, so heart or a spade. So so each suit has 13. So heart, it's never possible to have a heart and a spade at the same time. So that's going to be 26 out of where is my pen? 26 out of 52, or we can just say half, because if you reduce it, you're gonna get half. But if you just look at here, we have 4 suits, and these are equal in number. And heart and spade, that's 2 out of 4, and that's 1/2. Right? So it says a heart or a red card. Right? One thing to note is that heart is already a red card. Okay, so let's just assign events here. So say that H, event H is getting a heart and R is getting a red card. Red card meaning this is heart and diamond. Okay? Alright, so probability of heart or union, right? Red card is probability of H, heart, probability of red card minus probability of H and R. So let's look at these separate probabilities. So probability of getting a heart is 13 out of 52. Probability of getting a red card is 26 out of 52. And probability of getting a heart and a red card at the same time, that's just probability of getting heart. So that's minus, 13 out of 52. So this is just 26 out of 52, which is 1/2. Alright, so if you look at this diagram, this particular diagram, if you were to draw this in a Venn diagram, it's going to look something like this. Right? So this is for part D. This is, say this is red card and a heart. Okay, so a heart is already included within the red. Alright, so this is a Venn diagram and how it looks like. Alright, so let's move on to the next question. A single card is drawn from the deck. Find the probability that it is not a club. Alright, so not a club. Club, let's just notate that as a C. So getting a club is C. And we're looking for C bar, or we can also write this as C prime or C to the C. Okay, so this is going to be 1 minus probability of getting a C. Right, 1 minus probability of getting a club is 13 out of 52. And this comes out to be what? 39 over 52. Right? So neither, okay, so this time it's neither heart nor a 10. So again, H is heart and T is 10. Right, so it's neither heart nor a 10. So it's going to be the probability of H or 10, but complement of these two. Okay, so if you were to draw a Venn diagram, it's going to look like this. So we have H and T, but we're looking at this portion. Everything outside of the union. So pretty much everything outside of those two circles. Okay, so we're looking at this portion. And mathematically speaking, it's going to be 1 minus probability of H union T. H union T. So it's going to be 1 minus P of H plus P of T minus P of HT, and subtract that from 1. So let's look at this. P of H, as we said before, the same thing. That's 13 out of 52. P of T, there are 4 tenths, so that's going to be 4 out of 52. And what's the probability of getting both heart and a 10? That's just getting a heart and 10, so that's just 1 card out of 52. So here we go. This is all we have. So if we calculate this, this is going to be what is it? 17 minus, so 16. 1 minus. Alright, where is my pen? Okay, 1 minus 16 out of 52. And if you do that, that's going to be 36 out of 52. So that's the answer for choice B. Part B. Okay, so same thing. C. Why don't we just do a simple? No. Okay. I want to make some space for this. Okay. No. Sorry. Okay. I don't know why it's doing this. But this is supposed to be C. Alright? I know it's a little confusing, but alright, so neither red card or a 9. So let's assign the events again. R is going to be red, and N is going to be 9. Okay, so neither red nor 9. So probability of R union N and then prime. So this is 1 minus probability of R union N. Okay, so R union N is probability of R plus probability of N minus, oh sorry, this is supposed to be a P. Okay, and probability of Rn. probability of R is what? R is red card. There are half of them, so that's going to be, oops, 26 out of 52. I don't know why it's doing that. Let me just fix this. Okay, 52. Right? So probability of getting a 9 is there are 4 9s, so 4 out of 52, and probability of getting a red and 9. So for 9 there are heart 9 and a diamond 9. Right? So that's 2. That comes out to be 2. So we're going to do minus 2 out of 52. If you add these up, that's going to be 28. So 1 minus 28 over 52 equals, that's 24 out of 52. So that's the answer for part C. Okay? And let me fix this a little again. This is C. This and this is C, so this should be a D. Okay? And this is a C. Alright, so let's look at this. A diamond or not a king? Diamond or not a king? So let's look at this. Diamond. Okay, assign event again. So diamond will be D. And king will be K. So probability of getting a D. Union, not a king, so K bar. Okay? So, if we do this again, this is going to be same thing. Probability of D plus probability of K bar minus probability of D K bar. Okay? So probability of D, there are 13 of those diamonds, right? So 13 out of 52 plus K bar. K, there are 4 Ks. So if you do K bar, that's going to be 1 minus 4 out of 52 plus minus D and not K. Okay, so let's be a little careful. So K, there are 13 of diamonds, and we're looking at everything else except for the king. So that's going to be 12 out of 52. So if you do that, that's going to be 13 over 52 plus 48 over 52 minus 12 out of 52. So that comes out to be 49 out of 52. Let me see if I did the math correctly. Okay, seems right. And if you think I made a mistake or anything, just let me know, because I do make a lot of mistakes. So I'll try to fix those and let you know. Okay, and the last part is looking at a black king or not a black card. Okay, so let's be a little careful here. Let's say that A refers to black king and B refers to just black cards. And it says probability of a union B prime or B bar. Okay, and this is the same thing. Probability of A plus probability of B bar minus probability of A B bar. Probability of A is a black king, so that's there are 2 options, either club or a spade, so that's going to be 2 out of 52, plus probability of B, black, is half of those, so 26 out of 52 minus, we have to think carefully here. It says, what's the intersection between a black king and not being black? Alright? So, oops. So for probability of B bar, that's going to be not being black, so it's going to be red. But either way, that's the same because we have 26 out of 52, right? So here, where is my pen? A intersect B bar. Do you think that's possible? It has to be it has to be black king and not black. No, that's not possible. So that's going to be 0. And in fact, this is a case where these are mutually exclusive. Alright? So the answer to this question is 28 out of 52. Okay? So let's move on to the next question. And I believe that this was the second question. Let me see. Alright, so that was first, two. So this is the third question. Alright, so let me just fix the number. 3. Alright, so a die is rolled and find the probability of an even number. Alright, so even number, again, so let's just write the sample space for rolling a die. It's going to be 1, 2, 3, 4, 5, and 6. And how many are even? Half of those, right? 2, 4, and 6. So this is going to be 3 out of 6, which is equal to 1/2. Or a number divisible by 3. So number divisible by 3 is here 3 and 6, and that's 2 out of 6. Right? Or 1/3. Not a 2 nor a 6. So it's not a 2 nor it's a 6. So why don't we just do this? So let's just assign events. So T will be getting a 2, and S will be, okay, S will be, sorry, getting a 6. Okay, 6. So if you do this, it's going to be T, not a T nor a 6, so it's going to be T union S, but prime. Right, so this is going to be 1 minus probability of T union S. So if you look at this, it's going to be T plus S minus probability of TS. And what is that? 1 minus probability of getting a 2 is 1/6, right? And probability of getting a 6 is 1/6. And what's the probability of getting a 2 and a 6? That's going to be a 0 because these two are mutually exclusive. So these they add up to 2 over 6. The rest is 4 out of 6. And in fact, if you could have just realized that these two are mutually exclusive and just jump right into it, but I just did it because I just wanted to show you the assigning process. Okay. And here now we have not an ace. Okay, not an ace. I guess I would assume that ace is 1, because I'm not I'm not sure if there are any other than that. So let's just do this. Not an ace, so it's going to be the probability of getting a 1 is 1/6. So not an ace. It's going to be anything other than that. I don't know. It just changed the color by itself, and that's going to be 5 out of 6. Okay, so moving on to the last question. It says A and B are independent events, right? So A is 0.4 and B is 0.5. Find all these, okay? So why don't we just do this? If A and B are independent, we establish that if two events are independent, their intersection is actually the their um, product of their separate events, right? So if you're looking at this, PA is zero point 0.4 and PB is 0.5, so this comes out to be 0.2, right? So we have everything ready. Why don't we just draw a Venn diagram since it's a little easier. So no, A and B, we just established that the intersection is 0.2, so we're just going to write this here. And just A part, we have to subtract this from the A. So this is going to be 0.2 and here 0.3. Alright? And if you add them up, that's 4, 7. And everything has to add up to 1. So the outside part is 0.3, right? Let's look at this. P A union B. A union B is simply adding these numbers. So that's going to be 0.7. A and B, sorry, where's my pen? Okay, so A and B primes. So that's 1 minus A and B, right? So A and B is, again, 0.2. So 1 minus 0.2 equals 0.8. Intersect of A prime and B prime. Okay, so A prime, I'll show you two ways of doing this. So A prime is this part, right? Everything except A. And B prime is this part, right? So if you're looking at the overlap between overlap of yellow and blue, you figure out that the outside part, right? And that's what? 0.3. Okay? And you can also do this by the following. You can just, okay, so if A and B are independent, their complements are also independent. So you can just do A prime times B prime, right? So A prime is 0.6, so this is 0.6, and B prime is what? 0.5. So multiply by 0.5 gives you the same answer. So again, if I'll just write it down here. Okay, why don't I just bring this a little down. Okay, so here, if A and B are independent, their complements A prime and B prime are also independent. Okay? Alright, so moving on. Let's look at part B. Oops. Okay, so this is going to be D. It's asking for A union B prime. Okay, let's roll up a little so we can see the diagram. Let's look at this. It's taking a while. Let's just give it a moment. Okay, we're almost there. Alright, so let's look at this diagram. Alright, so it's doing this again. Okay. Oops. Sorry about that. Alright, so let's go down. A union B. So, okay, so A union B. This is, oh my god, this is, why is this doing this? So this is going to be probability of A plus probability of, oh, no, never mind. Let me erase this. It's asking for complement of the union. So this is talking about something else. Okay, so complement of union, so it's going to be 1 minus probability of A, B union. So this is 1 minus probability of A plus probability of B minus probability of A and B, right? We already know what union is. Let's move up a little. We already established that A union B is 0.7, so this is going to be 1 minus 0.7, which is 0.3, right? And now we have a probability of A prime plus probability of B prime and minus probability of A prime B prime. Okay, because we're looking for the union here. Probability of A prime, from the given question, we can know that this is 0.6. And probability of B prime is 1 minus 0.5, which is 0.5, minus probability of A prime B prime. Okay, and we already found that from part C, right? So that's 0.3, 0.3, so that's going to be 0.7 if I'm correct. No, sorry, I can do math right now. So this is going to be 0.8. Okay, so that's it for today. This is the classwork portion. So if you got anything wrong, just go over those, and I will include some problems. I would say like 2 to 3 problems to work on. So it's not going to take much time. Just go over those and catch up on any previous work from regression, correlation, or standard deviation, or all your so pretty much session 1 through 8. If you have anything to catch up on, just do that. Right? So I'll see you at Q&A session.